All right, everybody. What I'd like to do is talk about an extra credit problem that I gave on our quiz, which basically walks through the basic idea of deflate, which uses a Huffman coding followed by an LZ compression for data. What we're going to do is take this phrase, how much wood could a woodpeck pack if a woodpeck could peck wood, which I know is not the original phrase, and then compress it, right? See how low we can get it. Now, if you don't compress it, you have to send these 65 bytes uncompressed. And that would be fine. And for the duration of this video, I'm going to use kind of a down over up kind of underscore sort of figure for spaces. So what we're going to try to do is get this less than 65 bytes, or what is that, 520 bits, and see how well we do. We're going to fudge a few things here and there, but that's the general idea. So first thing we need to do is figure out the frequency of each letter, which I have kind of listed down here at the bottom. There's 12 spaces, 6 Ds, 1 MUI and F, 4 Es, 2 As and Hs, 4 Ks and Ps, 7 Cs, 7 Ws, and 13 Os. And I listed them in this order, not because it's great for Huffman coding, but because this is what my final tree is going to look like, so it'll allow me to draw the tree more quickly and make it look cleaner. When I first did this, it was a little messier, but once I knew what the final tree was going to look like, I reorganized the bottom to make it nice and clean. But if you're doing this by hand, it's probably not going to look that nice and clean from the get-go. So what you do is you always take the smallest 2 nodes in your tree and you match them up. So how come that's not drawing? Let's try one more time. There we go. So 2 ones make a 2, 2 more ones make a 2. The next smallest 2 are 2s, and we can do these 2 if we want. And then the next smallest 2 are 2s. We can do these 2 if we want. What we're doing is creating new nodes that then become eligible to be the smallest. So these 2 4s make an 8. These 2 4s make an 8. The smallest now are 4 and 6. We combine those and get a 10. The smallest now are 2 7s over here. We combine those and get a 14. The 2 8s are now smallest. We combine those and get a 16. Looks like 12 and 10 are the smallest now. We combine those and get a 22. 13 and 14 combine to give 27. 16 and 22 combine here to give us 38. And then 38 and 22 combine to give us 65. And it's good that we get 65 up here because that was the length of our original message. Now, how does this work? If you go left, those are zeros. Let's do that in a different color here. Those are zeros. Every left branch is a 0. And if you go right, those are 1s. And this tells you what the bit encoding is of everything in the tree. So 0, 0, 0 is a space, right? And we can form the whole tree. We can form the whole encoding for every byte at a much smaller rate using this tree. And you'll notice that all of these are smaller than the original. That's not always the case. Sometimes there will be some elements down here, like things that only occur once, that might end up being longer than your original encoding. But the idea is that because the higher frequency is so much smaller, you save more space in the end. And sometimes that happens when you're dealing with really small message sizes or really big message sizes that have higher frequencies of things like the letter E in the English language or something like that. You can see over here that O is encoded with just 2 1s, which is great. So let's write down what those bit sequences are. I might get a little small here for everything. So, So O is 1 1. Space is 0 0 0. C is 1 0 0. W is 1 0 1. D is 0 0 1 0. E is 0 1 0 0. And remember, Huffman coding does a prefix thing, so any of these prefixes that we see means that once we see 0 1 1 0 coming from left to right, we'll never see that again in another character. 0 1 0 1 0. 0 1 0 1 0. Getting long, huh? 0 1 0 1 1. They're all still shorter than 8 bits, which is nice because it means we should be saving space no matter what. 0 0 1 1 0 0. And then we get to U, which is 0 0 1 1 0 1. which I didn't write there. And I is 001110. And F is 001111. So this is our encoding. These are the bit sequences that we'll use for these letters from here on in. So we will have to send this dictionary. The fudge factor that we used to send this dictionary was that we'll send each character, which is 8 bits, followed by its sequence, which is however many bits that is. So in this case, it's 2 bits for the letter O. And then we'll send a kind of fudge factor 2-bit separator. Now, in reality, we can actually send the Huffman tree. We don't necessarily have to send these bits like this. And the Huffman tree might actually save us a fair amount of space. I think when I did this problem, it ended up significantly saving us space compared to how I'm fudging this dictionary cost. But that's okay. We'll stick with this for now because that's what I threw into the extra credit problem. But we could actually encode the tree more directly. So in total, this is going to cost us basically 10, 12 bits. And then each of these will be subsequently, just a little bit more. So 12, 13, 13, 13, 14, 14, 14, 14, 15, 15, 16, 16, 16. And you might say, well, this last one won't cost us the extra 2 bits for the separator, but we're going to use that to separate the 2 dictionaries. So we get a total to send this dictionary, which looks like this, according to our technique, which isn't necessarily the best. And we'll need to add all of these things up. And in total, you'll end up with whatever this number is, which we can do here in a second. Or, well, we can do it now. That's fine. Let's see. We got 39. It looks like 12 plus 13 times 3 plus 14 times 4 plus 15 times 2 plus 16 times 4. And I did it this way because these numbers actually come out to be pretty cool. Right? Looks like that. So this is 51. This is 86. 86 and 64 is 150. So I get about 201 bits here for the dictionary, for the Huffman coding dictionary that we'll have to send. Now, at a minimum that you're going to have to send these 14 characters to tell them what the encoding are, and that you'll have to send you might not have to send all of these bits if you can send the tree. But at a minimum, you would have to send 132 bits. So this is a little bit bigger than that at 201. But we are still saving a little bit of space, as you'll see here in a minute. All right, so 201 bits to send the Huffman coding dictionary the way that we described it in the extra credit problem without sending the tree. So then what we need to do is the LZ compression. And the way the LZ compression works is we basically want to find common phrases in the original phrase to encode and index as a dictionary. So I picked out 1, 2, 3, 4, 5, 6, 7. I picked out 7 phrases, which means our index needs to be 3 bits long because 7 things need 3 bits. And then I wrote down how many times they appear. So wood appears 6 times, peck followed by a space is 4, space A space is 2, space C is 2, and then the rest only show up 1 time. And so what's going to happen is when I encode this, when I write this sentence, I'll write the word, the bits for how, which is 100, followed by the bits for much, 110, followed by the bits for wood, right? And this is how I would write this message, followed by the C, followed by wood again, followed by the A, followed by wood again, followed by peck space, followed by peck space. And I'm down to if now. A, wood, peck, C, wood. You see wood show up again. Peck, and then wood. There's no period here. So you can see this is the actual bits of my message now after it's gone through the dictionary. So I can tell this before I even do the Huffman coding of the bits. The Huffman coding of the bits, what it's going to do is shrink the size of this dictionary send. So what we said for this dictionary send is we would send the Huffman coded bits followed by some 2-bit separator, which is going to add 14 bits at the end. So all we have to do is figure out how long these phrases would be based on how many bits each of these characters is. So like W is 3 bits, O is 2 bits, so this is 3 plus 2 plus 2 plus the D, which is 4 bits. So it's going to cost me 7, 8, 9, 10, 11 bits to send the word wood, followed by the 2-bit separator. And then I'll do the same thing for peck and figure out what that would be. So I will send P, which is 4 bits, then E, which is 4 bits, and then C, which is 3 bits, and then K, which is 4 bits, and then space, which is 3 bits. And so I get, it's a little hard, right? Because I'm trying to look at this table at the same time. And so the way that I actually did this is I used 2 screens. Let's delete this computation here, 201 bits of the send, and let's copy this table up here so that we can do this and see them together. How about that? All right, so let's copy this table, and we'll figure this out so that we can see all of this together and make it bigger and give us more space here. Okay, so what was our total here? 8, 12, plus another 6 is 18 bits, let's say. All right, how about space A, space? Space is 3, the A is 5, plus another space, that's 11 bits here. How about space C? Space was 3, C is 3, that's only 6 bits here. How about how? That's 5 plus O plus W, and I'm just counting bits here for how many bits it's going to require me to send these. So it's 6, 7, 8, that's 13. How about if? If is a big 6 points, plus if the other F is 6 points. How about much? We've got 1, 2, 3, 4, 5, 6 plus U plus C plus H plus space, much space, equals 12, 15, 23. Okay, so don't forget about these 14 bits for the separators, but we're going to add all these up. We get 29, add these, you get 40, 46, 59, 71, 94, plus the 14 that we have left over, gives us about 108 for this dictionary. Okay, so what's left? What's left is we have to actually send the message itself. We already wrote down what that message is. It turns out that because we know that this is a number of characters we know how many times each of these things appears and that each of them is 3 bits long. We know that this is 51 bits, but we can just add these, right? 3, 6, 9, 12. Well, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 times 3 is 51 bits. That's a 5 there. So in total, to send this message, the way that we've encoded it and cheated some of this here, we have to send 201 bits for the original dictionary. That is the Huffman coding tree, not the original dictionary. Okay, so we have to send each character followed by its bit sequence, followed by a fudgy 2-bit factor. And actually, this number might be a bit smaller, but it's not going to be a lot smaller because 136 bits is required to send the characters in general. 132, 112. I don't know, some number. Then we have to send this dictionary, which we computed as 108 bits. And then we have to send the actual message. So in total, to send this message, we've come down from 520 bits all the way down to whatever this number adds up to, which is 360 bits. Wow, did that in under 15 minutes. Amazing. 360 bits is what I get here. That's not too shabby, assuming I did most of this correctly. Let's see if it matches what I have sitting over here in my Excel file. It looks like it mostly matches. For some reason, I have 364 written down, but I do have 201, 51, and 108 written down, so I'm not sure where the extra little bits are coming from. But there it is. Amazing, right? I may have sent the separator twice, and that's where my extra 4 bits are coming from, and that was a mistake in the original one, not in the one that I just showed you all. So we can take a message like this, break it down into something like this. Now, this 2-bit separator fudgy factor might actually get a little bit better if you use the proper postfix send for this tree, which would allow you to send, let's see, it would see 14 bits plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 27 bits plus the, how many were there? Were there 14 characters in total? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 characters in total times 8, which is 80 and 32. It's 112. So actually, we can get this down to 139 bits. But then you have to think about how we send this. So there might be some more savings that I cheated us by doing this dictionary this way in our extra credit. But that's where all the numbers come from. Hopefully that was fun and exciting for you. I really like it. It's really crunchy, and it's really interesting to see how some of these methods work. The bit sliding window might actually be able to do a lot better than this. It'd be interesting to throw this into the DEFLATE algorithm and see how small the final message is and what those actual details look like. That would be fun. But that's all I've got for this. This is the how I came up to the answer for this problem. Hope you have fun. I did. See you all next time. Take care of yourselves and make sure you take care of each other. Okay, bye.